What I hope to do in this video is get even more algebraically familiar with the Lorentz transformation so that we can recognize it in its different forms and start to build our intuition for how it behaves. So let's just write down the Lorentz transformation, or at least the way that I like to write it. So let's just remind ourselves, if I'm in my frame of reference, I'm floating through space. So I could say S for Sal's frame of reference. Some event in space-time from my point of view, it's going to have some x coordinate. I will do that in green, and it's going to have some CT coordinate. I could do that in orange. Let me do that in orange. So the Lorentz transformations are going to go from coordinates in my frame of reference, space-time coordinates for an event, to my friend's frame of reference. So we could say that's the S prime frame of reference. And in her frame of reference, the event will have space-time coordinates x prime. Let me write it this way. x prime, comma, ct prime. I'm really having trouble switching colors today. ct prime. And so let's just write it down the way I've written it down in the previous videos, and then I'll do a little bit of algebraic manipulation so we can recognize its different forms. So if we want to get x prime, so we want to figure out x prime, we see that it's going to be based on the Lorentz factor times x minus a scaled version of ct, and the scaling factor is beta, and we will redefine beta in a second. So beta times ct, where our Lorentz factor, let me write it over here, the Lorentz factor is 1 over the square root of 1 minus v squared over c squared, or we could write it as 1 over the square root of 1 minus beta squared. 1 minus beta squared, where beta is equal to v over c. So there you go. That's how we get x prime, and it's going to be based on the Lorentz factors dependent on v, and of course the rest of this is going to be dependent on x and ct. And so how do we get ct prime? Well, ct prime is going to be equal to, I'll just write it right over here, ct prime is going to be equal to the Lorentz factor times, and once again, this is going to be the nice symmetry we talked about, times ct, let me do that in orange, so ct minus beta times x, beta times x. And like I've said before, I like to write it this way. I find it easier to remember. And I find it easier to remember because it has this nice, beautiful symmetry to it. When I'm solving for x prime, it's x minus beta times ct. When I'm solving for ct prime, it's ct minus beta times x. And in both cases, I'm scaling by the Lorentz factor. But let's manipulate this a little bit just to understand a little better and reconcile with what you might see with other sources, including, say, your textbook. Well, we know that beta is equal to v over c, and this is v over c. And so we could write this as we have v over c times c. This c is going to cancel with that c, and so we could rewrite this as x prime is equal to the Lorentz factor, gamma, times x minus vt, x minus vt. V times t. Now this is really interesting right over here, because if you ignored gamma, or for gamma was 1 here, this is essentially the Galilean transformation. You wouldn't have, if it was just x minus vt, that was what our intuition about our everyday life, about Newtonian physics, would actually tell us. And so when you view it in this form, you're really saying, okay, well, we're just going to scale that by this Lorentz transformation, which has this interesting behavior that if v is much, much smaller than the speed of light, well then this whole factor is going to be pretty close to 1, and that's why the Galilean transformations worked for us for kind of everyday velocities. But then if v starts to approach the speed of light, this thing blows up, and we get a very different result than with our just traditional Galilean transformation. Let's think about what happens over here. And over here, instead of staying in ct prime, I'm going to also divide both sides by c. So we're just solving for time as we normally associate it with, not just the t prime variable as opposed to ct prime. So let's also divide both sides by c. So you divide by c there, and you can divide by c there, and you can divide by c there. Those c's cancel, those c's cancel, and so we're left with t prime is equal to the Lorentz factor, times t minus, now you're going to get v times x, and you're going to divide by c twice, so over c squared. So vx, v times x over c squared, And this is actually a more typical way, both of these, of seeing the Lorentz transformation. The reason why I don't like this form as much, even though this does have the neat kind of, when you look at it, it looks like you're just scaling up the Galilean transformation, is that you no longer see the symmetry there, and you should see the symmetry there because we're talking about space-time. We're not talking about this independence of space and time. And we saw how the angles in the Minkowski diagram, how those were symmetric, the angles between the regular or the unprimed axes and the primed axes. And so what I don't like about this is you no longer see the symmetry, while you did see it the first way that I wrote it, and I find this harder to remember. But let's just think about what happens here when v is a very small fraction of the speed of light. Well, as we already said, our Lorentz factor is going to be pretty close to 1. And if v is a very small fraction of c, well then this second term right over here is going to be pretty close to 0. And so if v is a small fraction of c, then this thing is going to get pretty, so let me write this down. So if v is much less than c, then this is going to reduce to t prime being approximately equal to, because our Lorentz factor is going to be pretty close to 1. This is going to be pretty close to 0, so this is going to be pretty close to t. Likewise, for v much lower than c over here, our Lorentz factor is going to be pretty close to 1, and so x prime is going to be approximately equal to x minus vt. So for small v's, and small could even be, the speed of a bullet, or even the speed of the space shuttle, or things that are just much smaller than the speed of light, 3 times 10 to the 8 meters per second. Well, that's why the Galilean transformations are pretty good approximations. So hopefully this starts to give you a little bit of intuition. Start evaluating this. Evaluate this for v's in our everyday life, and then see what happens when v starts to approach 0.8 times the speed of light, 0.9c, 0.99c. Think about what happens to the Lorentz factor, and hopefully you'll get an appreciation for how this whole thing behaves.